So, ladies and gentlemen, it's a great pleasure to announce Professor Lyudmila Turowska from Chalmers University of Technology and University of Gothenburg. And she will speak about Shilov boundary for holomorphic function on a quantum atom board. Please, Professor.
Thank you very much. Thank you very much to organizers for giving me the opportunity to talk here. So I'm the first time in Bedlaros, so I'm very happy to be here. Thank you. So this is a joint work with Olga Bernstein, who's in the University of Copenhagen, and my student Olaf Giselsson, who is in Chalmers also. And this will be about some complex analysis, quantum complex analysis. I will give a definition of the Shilov boundary, and I will explain all these words here. Let me start with the known result, which we teach our students. This is the maximum modulus principle in complex analysis, which says that if we have f is a holomorphic function on the unit disk, which is continuous up to the boundary, then we have that this function f in this holomorphic function, it has its maximum on the boundary, on the unit circle t. Okay, so and we have also the t is the minimal closed subset of d, which satisfies this equality, and in this case we call the t is the Shilov boundary of the unit closed unit disk related to the algebra of holomorphic function of t. So more general definition is given by Shilov. So we consider X to be compact Hausdorff space, and we consider A to be a uniform subalgebra of C of X, which means that A is closed, contains constants and separate points. So it's not closed on the complex conjugation, so otherwise it would be the whole C of X. But it generates, as a C-star algebra, it generates C of X. The Shilov boundary of X relative to this algebra A is the smallest closed subset K in X, such that the norm, the maximum norm of this function f on C of X is equal to the maximum of f of X on this closed subset. I will need some equivalent reformulation because I'm going to quantize this notion of Shilov boundary. So if I denote by J this closed ideal, so all functions which vanishes on this closed subset K, and consider this maps J, the quotient map C of X to the quotient C of X by this ideal J. So this equality, it means that this J is an isometry when I restrict it to the algebra A. So now I'm going to quantize to define the quantization of the Shilov boundary, and it was proposed by Arvidsson in his ACTA paper in the 70s, so it was a very influential paper. So I replace the commutative C-star algebra C of X by just unital C-star algebra B. So this is a non-commutative topological space. Then a closed subspace I replace by a closed ideal in B. And the uniform algebra, so I will consider subalgebra A that generates the C-star algebra and contains one as the unit element of the B. Okay, one define, so Arvidsson defined the Shilov boundary in the following way. So we say that J. So first we define the boundary ideal. So we say that an ideal J, closed ideal J in B, is a boundary ideal relative to this algebra A. So A is not closed on the involution, so just some subalgebra. So if the canonical solution map from B to this quotient algebra is an isometry, but I add this word complete isometry when restricted to A. Complete isometry means that so if I have a C-star algebra, so I can consider matrices with entries in B, and I can extend and matrices of this quotient, I can extend this J to matrices, just applying J to each entries. So on matrices on C-star algebras, this algebra, it has a canonical C-star algebra, the unique C-star algebra. So, and I want that this J is not an isometry, only isometry from B to this quotient. I want it to be an isometry, the extension of G, it will be an isometry from Mn of B matrices over B to matrices over B over J. So that means that this is a complete isometry. So, and I want it to be complete isometry, not on the whole B, it cannot be, but I want it to be the isometry when I restrict it to this algebra A. And the boundary ideal is called the Shilov boundary ideal if it contains any other boundary ideal. Okay, so if I have B is the commutative C-star algebra, that is C of x, then this complete can be removed. So any isometry, it will be automatically a complete isometry. So it's really the extension of the classical notion of the Shilov boundary. Yes, so Shilov boundary ideal was, as I said, introduced by Arvidsson. Arvidsson showed that it's unique, and he left open the question about the existence. He showed the existence of this Shilov boundary for some particular examples, but he could not prove it in general. And only in '79, Sohamana, studying the existence of injective enveloping algebras for operator systems, he could prove the existence of the Shilov boundary. And then later, so 2003, so Drichel and Markulo, so they reproved the existence of Shilov boundary using the dilation theory. And this was the original idea of Arvidsson, that this notion should be related to the theory of dilation. And this dilation will appear in my talk soon. Okay, so another example of Shilov boundary, which will be important for us, is the following. So we consider the matrix balls. So we consider n by n matrices, and we consider all matrices such that the norm of Z is less than 1, or Z star is less than 1 as operator. And we consider the DFU. So this will be just the unitary matrices. So I consider continuous functions on the closure of this unit ball. I consider continuous function on this unitary matrices. This is a commutative C-star algebra of continuous functions. And the AFU, so I will again consider the algebra of holomorphic functions in this complex domain U. And then we consider J from CFU to this one. So this is just the restriction map. This CD of U is just the quotient of this continuous function by the ideal of all function which vanishes on this D of U. So this is the restriction map, and the classical series, so it's known that there is this maximal principle, even in this case, which says that J restricted to A of U, it will be an isometry, and since this is a commutative, so it will be a complete isometry, and therefore J is a boundary ideal, and even the Shilov boundary ideal. Okay, and so what I want to discuss Q analog of these C-star algebras, continuous function on the matrix ball, and continuous function on unitary matrices. So I want to construct this GK, GQ, this is analog of this restriction map, and I want to show that the kernel of this map GQ, it will be the Shilov boundary. Okay, so this Q analog of this matrix ball, functions of the matrix balls, it was introduced by Waxman in 90s together with his courses. This is the paper, the first paper on Q analogs, and there is a monograph, quantum bounded symmetric domains, published 2010. So he introduced this object he had a program to quantize bounded symmetric domains, and the algebra of functions on the quantum matrix ball appeared within this program. And he asked me about this question about the Shilov boundary for this object. I could not prove that time. I didn't know. Somehow I could manage. Only recently I found a way how to deal with this problem, and I was very happy to get a result in this direction. So let me introduce the object. So first he defined this algebra, the Q analog of polynomials on matrices, and then continuous function on the Q analog continuous function on the matrix balls. It will be obtained as a completion of this algebra with respect to certain norm. Okay, so first we will define its holomorphic part. So we can see the function on the Q analog of function on the matrices or polynomials, holomorphic polynomials of the n by n matrices. So this is an algebra with generators that ij, which satisfies some Q commutation relations, some relation with this parameter Q from 0 to 1. This algebra is quite known in quantum group theory, so we will call it Q analog holomorphic polynomials on matrices, n by n matrices. Then polynomial algebra, so it will be Q analog of polynomial algebra on matrices, and so we need to add some non-holo or anti-holomorphic part. So this will be an algebra with generators that ij's, which we have here, and we add that ij star. So it will be a star algebra. So these star generators, they will satisfy similar relation, but we have to take the involution over all these relations. And we need also a relation between holomorphic generators and anti-holomorphic generators. And these are the relations. So they look quite complicated. So these are coefficients, so some coefficients coming from R matrices corresponding to quantum UQSLN. Okay, so relation is quite complicated. If one wants to so in order to define a continuous function, some kind of analog of continuous function, we need to define a representation of this star algebra. And if we just try to do it by hand using these relations, it will be very complicated. So we have to use somehow a symmetry, some quantum symmetry of this algebra, and in order to classify this. Give some representation of this algebra. So as I told, this algebra was introduced and studied by Waxman in his courses in the 90s. So if I take n to be equal 1, so this is quite well-known object, so it's called quantum disk or Q commutation relations. So this algebra is generated by just one generator satisfying this relation. So representation theory is known, and the universal and consist algebra of this object is also well known. So in order to define the Q analog of the Shilov boundary, so if you remember, so the Shilov boundary of the matrix ball in the classical case Q is equal to 1, so it was just unitary matrices. So it's natural to expect that Q analog of the Shilov boundary in this case, it would be quantum unitary matrices. Okay, so let me introduce this object of quantum unitary matrices. So if I form matrix out of generators of my algebras that I chase, so I define the quantum determinant. So in this way, so if Q is equal to 1, so it's just the usual determinant of an n by n matrix. So one knows that the Q determinant is in the center of this holomorphic path, C mat and Q, and the localization of this algebra with respect to the powers of that Q set is the algebra, is called the algebra of regular function on the quantum GLN, and it's denoted in this way. So it's quantum invertible matrices, or algebra of functions on quantum invertible matrices. On this algebra, so there is a unique involution star, which is defined in this way. So here, set AB is a matrix which we get from this matrix C by just deleting the row B and the column A. And yeah, so again, if Q is equal to 1, so this element here, so it's just the AB element of the inverse of the matrix. Okay, and we define the algebra of polynomials on what we will call the Shilov boundary. This is just this star algebra, so we take this GL and Q, this localization of matrices, Q analog of matrices, regular function of matrices, n by n matrices with this involution star, and this is also to be isomorphic to the object which is known the algebra of regular function on Q analog of regular function on unitary matrices. Okay, and Waxman, he constructed this homomorphic, star homomorphism from the algebra of polynomials, Q polynomials on matrices, n by n matrices, to this algebra, just sending generators that IB in here to the same generators which we consider in here. So, and he proved that this would be a star homomorphism. So this GQ, so this is just the Q analog of the operator which receives polynomials to the Shilov boundary. Yeah, and we want to show, yeah, so first we want to construct, so here is just polynomials, so we will complete this and define the Q analog continuous function on the matrix pole, and then we want to extend this GQ to the C-star algebra, and we want to show that the kernel of this GQ, it will be this Shilov boundary. Yes, so in order to work with this algebra, so we, as I told, it has some kind of quantum symmetry, so it has a coaction of this quantum group. So this quantum group, so the algebra of regular function on quantum SUN, this is just this quotient, so the quantum UN and the quotient with this ideal. The more natural generators for this group is this TKJ. So having this generator, so you'll get that this object, it's a Hopf algebra, it's a quantum group with a coproduct delta, which is defined in this way per unit, and it has an antipode. And there is a coaction of this quantum group on this algebra, which is given by this homomorphism, this homomorphism D, given by this formula. And it's, if Q is equal to 1, so this coaction comes from the two different actions of SUN on the algebra of matrices, just the left multiplication and the left multiplication and right multiplication by the transposed matrix for A SUN. Yeah, so in order to define a cyst algebra out of this algebra, so I need some representation theory. There is a special, so the word fork is also here, so there is a very special representation, which we call fork representation of this algebra. It's defined in the following ways. So we consider Paul mod NQ model H, which is determined by the generator B0, which we call the vacuum vector. And this vacuum vector has a property that it's annihilated by all anti-holomorphic generators. So ZA B star, so V0 is equal to 0. And Sinevchik, Shilov, and Waxman, so they proved that on this H, on this vector space, one can introduce a unique ciscollinear form such that this action of Paul mod and Q on H becomes a star representation. And it will be, so H becomes a pre-Hilbert space, and this operator, which I will denote PF, F is for the fork representation, which is given by sending the vector B in H to the action F by D. So this action, it will be bounded with respect to the norm on this H coming from this inner product. And therefore it can be extended to a bounded operator on the completion H bar. And this representation, it will be called the fork representation of this star algebra format NQ. Yeah, so I want to have some nice description of this fork representation in order to work with it. So for this, I need some kind of embeddings. Yeah, so for example, if I have m is less than or equal n, so I can always embed Paul mod NQ into Paul mod NQ in this way. So in particular, I will have this star holomorphism from Paul mod n to Paul mod 2NQ. Then we have a star holomorphism from Paul mod NQ to this one, quantum group, which is given in this way. So, and therefore we have a star holomorphism from this, our algebra Paul mod NQ, to this quantum group, which is given in this way. So representation of this quantum group is very well known, so we want to use representation of this quantum group to get representation of this algebra. And in particular, we want to find whether representation of this, some representation of these quantum groups can give us this special fork representation of this algebra. So the idea is to construct a star representation pi of this such that the composition pi with this holomorphism will give us this fork representation. Yeah, and it's possible to do. So, but first I want to give some introduction to the star representation of these quantum groups. This quantum group C, S, U, and Q. So a very nice theory. So it was given by Soberman, and it's as follows. So if I take n is equal to 2, so irreducible representation can be nicely described. In particular, we have this representation pi, which is given in this way. So this algebra, it will have these 4 generators. And the representation given in this way. So S is just the isometry, CQ and DQ some diagonal operators. And this one can show that these diagonal operators can be written as a function of this isometry and its adjoint. In particular, so we have the cyst algebra generated by this isometry S, it will be the same as the cyst algebra generated by S, CQ, and DQ. This algebra is also called the Toeplitz algebra, so this isometry algebra generated by the isometry. Okay, and then let's consider also the following homomorphism. So from SUNQ to SU2Q, so which is given in this form. So in principle, so it's invariant of SU2 in SUM in such a way so that we put SU2 in on some diagonal. Okay, and now we can get representation of SUM combining this homomorphism, star homomorphism pi I and this representation pi. So composition pi and phi I, so it will give us a representation of this SUMQ. And actually, any representation can be obtained out of this composition pi and phi I. So namely, we have the following. So if I denote by pi, this is the composition pi and phi I. And if I consider Si, this is the transposition which changed the I and I plus 1. So in particular, I will have it pi I. So the image, it will be in this cyst algebra, so for me it will be important. And then for each element S in Sm in the symmetric group, I consider a minimum decomposition into a product of the transposition and consider pi S to be star representation of this quantum group given by this tensor product. Okay, so this is the quantum group, so it has the co-multiplication. So this tensor product is just the composition of the co-product, and then we apply this Pj1, Pj2, Pjn tensor product. Okay, and the result of Soybenman says that up to unitary equivalence, this pi s is independent of the specific minimal decomposition, and up to the action of the torus, so we will have that these are all irreducible representation of this quantum group. So very nice description, so that one can work with this. So now back to the Fock representation. So we want to have the Fock representation. In some way, we want to obtain it from the representation of SU2n. So we consider in the symmetric group S2n, so the following element, special element. Then we have that S can be written as a product, so this minimal decomposition. Minimal decomposition, it will be can be written in this sigma 1, sigma n, whereas sigma a, this is our transpositions. And we have this psi, this composition psi rho, so it was a star homomorphism from holomorphic n to SU and Q. And then if we take the composition of this star homomorphism with this specific representation of SU and Q, so we will get this Fock representation. And the image of this Fock representation, it will be in the tensor product of this Toeplitz algebras and squared copies of this tensor system, Toeplitz algebras. Okay, yeah. And actually this is also true in general, so any representation of Holomorphic and Q can be obtained in this way. So there exists a star representation of this quantum group such that P is unitarily equivalent to this composition. And we have a nice classification of this all irreducible representation of this algebra by a conjugated algebra. Yeah, and the result also of my students saw that the universal enveloping cyst algebra of this holomorphic and Q, it will exist, and it will be isomorphic to the image of this special Fock representation. So we have all description of all representation. We have that this enveloping cyst algebra is just isomorphic to the image of this very special Fock representation. And this, the existence of the universal enveloping system algebra follows from Waxman remarks, so that if we have a Fock representation, so then if I write the Z to be this matrix, so I will have the norm of this, I apply PF to each generator, so that the norm it will be less than 1, which is universal. Okay, so we have the theory of representation. So now back to the Shilov boundary. Yes, so this will be this universal enveloping algebra, which is isomorphic to the image of this special Fock representation. So we will call a Q analog of continuous function on the matrix ball. Why we call it? Why this universal enveloping algebra will be called Q analog of continuous function on the unit ball? It's because of this. If we take this matrix, so in Fock representation, it will satisfy that the norm of this matrix, it will be less or equal to 1. Okay, so the Q analog of holomorphic functions on this UN, should be UN, is the unital closed subalgebra, which is generated by this holomorphic coordinates. So we take image in the Fock representation of this holomorphic coordinates, and then we generate an operator algebra, not a star algebra, just operator algebra. So it will be a Q analog of this holomorphic function. We have this algebraic Shilov ideal. So this is what we have from Waxman's result. So he constructed this GQ, this homomorphism from these polynomial algebras to this polynomial algebras. So it's given in this way. So for n is equal to 1, so this is the ideal generated by z star minus 1. And for n is larger than 1, so we have this more complicated expression. And our theorem is that if I take this ideal G, so this is the same as Gn, so, and take the image in the Fock representation and take the closure in this algebra, so I will have that this would be a Shilov ideal in the sense of Arison, which means that this map, which I extend, this map, the quotient map, this natural quotient map, it would be a complete isometry when I restrict to this holomorphic path, and this Gn, the closure of Gn, it would be the maximal one with this property, so it will be actually the Shilov one. And let me just talk a little bit about the idea. So I told that this must be related to dilation. Must be related to the dilation. Yes, so the idea is the following. So if I have PF, and this is my Fock representation, and Gn is just the algebraic Shilov boundary ideal. So to see that this would be a boundary ideal, so it's enough to see that PFN is a dilation of a star representation psi n of this my algebra that annihilates this algebraic ideal when I restrict it to the holomorphic part, which means the following, so that I can find a representation of holomat NQ on a bigger Hilbert space, such that this Fock representation, Fock image of this, it would be this restriction. So I restrict to the H Hilbert space, and then I take the restriction also by multiplying by projections to this Hilbert space, and I must have the equality. And why this is enough? Because the following. So if I have now this element, this matrix element in this algebra, because I have here these projections. So I clearly, the norm of projection is less than 1, so I clearly have this less or equal than the norm of this element. And then since psi n, it annihilates Jn, so the norm of this, it would be less than the norm of this element in this quotient algebra. And then I can also continue here and write less, so equal the norm of this Pmn. So actually all the way here, so I will have the equality, and this will give me the complete isometry. And yeah, for this I will use the induction, and the induction step, this is the classical Sekal-Nagis dilation theorem, so which says that if I have a contraction, so a construction can always dilate it to a unitary operator. And not only T can be dilated to unitary, but all powers can be dilated to unitary. And this gives me the following. So if n is equal to 1, so this is my reduction step. So this algebra, so it's generated by this operator T, which is the image of this unique generator of the algebra. And the image of this, it's given by this shift, weighted shift, and this clearly this would be a contraction, and therefore I can, for any polynomial p, I can write p of t as a dilation of this same polynomial p on some unitary operator. And then this representation which sends z to u, so it will be a representation of my pole mat 1 or pole CQ. And it will annihilate this Shilov, algebraic Shilov boundary, so I will get that my Fock representation, it will be the dilation of this, and this would be enough to say that it's. Then for induction steps, so I just there is some reduction from n to n minus 1 which will be used, and so this invariance can be used, and one can prove the statement. Let me just finish with some questions. And so the questions, so we have this Shilov boundary for matrix ball. So there are other quantum symmetric boundary domains. There is a classification. There is a list of these algebras, polynomials on the corresponding complex spaces. So at the moment, so I have these some master students. We have described the Shilov boundary domain for QNR holomorphic function on the unit disk of 2 by 2 symmetric matrices. So, but we don't have a general theory for other. And then the question, can one describe this Shilov boundary ideal? So what would be this? In case of n is equal to 1, so it's just the compact operators. And we know that the universal enveloping algebra, so it would be just the Toeplitz algebra, and the Toeplitz algebra by compact operators, just a continuous function on the unit circle. We don't know what would be in general case. What would be the properties of this algebra? So we know that it's type 1. So it would be nice to know the dependence on Q, how it works with Q. So if n is equal to 1, so it's known, so all these algebras, sister algebras, so they will be isomorphic, and they're isomorphic to the Toeplitz, to algebra of Toeplitz operators. For n is equal to 2, so we could prove that they will be all isomorphic. So it will be, But for larger n, so we don't know what it will be. So we have some hope to show that they will be isomorphic.
Thank you very much for the nice talk. I think the problem in the problem session, so maybe you can repeat in Friday more details because we have no time now. But maybe some now, one, two question, remark.
What about the one-dimensional representations? Are they found here?
Yeah, so there are.
There are, but you didn't mention that.
Yes, there are one-dimensional representations. It's quite easy to describe. So.
Yes, but they do not play a role here, or? In Zögelmann's has only the infinite dimension.
I don't, well, nothing specific. So the representation which annihilates this Shilov boundary, so this is important. So, and the all one-dimensional, they will be among those.
Thank you. Are there any questions? I have a small question about the determinant, because your parameter Q is between 0 and 1.
Yeah.
So yeah, but and for us, we work with Roland Speicher some ideas about Brownian motion on quantum group of Holonovich, SU2N, and we need positivity, that for positive definite matrix Zij, the Q determinant is positive. Did you need positivity result in your job? Or maybe follows from that? Maybe you answer if we have time, but anyway, positivity result will be if you have in your business or not.
Yeah, well, in irreducible representations, it will be just a number, positive, it will be positive numbers. So
no, but I mean for positive definite matrix, Zij,
yeah.
we prove that Q determinant is positive, even Q minus 1 to 1. Also, you don't consider minus negative.
No.
Okay, thank you once more. So, thank you once more.